Hello, I am your annoying engineer friend and I welcome you in this video in which we are creating a portal frame parametrically in Grasshopper. If that sounds interesting to you, stay right there. Okay, to start, we are creating the base point with construct point component. It has 3 inputs, x, y and z. Into each, connect a number slider. Let's name the first one global x and set its accuracy to 3 digits because we are in meters in Rhino, and to make a millimeter precise structure, this accuracy is required. That means we are using floating point numbers. As for the maximum, set its value to 100. By holding down the Alt key, we can copy any component to Grasshopper, resulting in global y and global z in our case. We got the base point now, let's create another one utilizing the move component. It has 2 inputs, geometry and a motion, which is basically a vector. Geometry will come from the construct point, and for the motion, take a unit x. For this, create another slider and name it frame width with a maximum value around 15. Double-clicking on the slider, we can set the exact value for set slider, for example 8. Next step is to copy these points in the z direction, meaning upwards. We achieve that with an additional 2 moves. One's geometry is the construct point one, the other's is the first move. Take a unit z, which will give direction to them. Another slider for the unit z, this we can name height and give a maximum around 10. To create the apex point, we move the very first one in the x and then in the z direction. We have 2 options here. Either we use a pair of unit x and unit z, or we take a fancy tool called vector xyz. Regardless, it needs numbers for its inputs. The next slider's maximum value will be 1 because this will be our ratio. With the multiplication component, which will have for its input the frame width and the ratio, we can set where exactly the apex point will fall in between the 2 sides if we don't want to be right smack in the middle at all times. This is the x input. Take an addition in which we are adding the height and another slider called apex plus height together. Set this new slider's maximum around 5 and connect its output to the z input. We need another move now. From the construct point, take the geometry with this vector, and this creates our apex point. Utilizing a merge component after these 5 points, we can quote-unquote group these points. First should be the one from the construct point, the second is the one that sits above this, meaning that one. Next comes the apex, followed by this, and for the last one, it's this. To create a 3-dimensional structure from the group, we have to specify distance for these frames and the number that will tell us how many do we want. It's another 2 sliders. This is base distance, and the second one is an integer slider with a name, base number. With the help of repeat data, we can create a list that contains the distance value as many times as we have set on the integer slider. The output goes into mass addition, which in simple terms sums its inputs. We can see the final result or the result of the calculation with every step included. This is what we need. Take a unit y, which converts the numbers into vectors pointing in the y direction. Then it is another move with a unit y as the motion and merge as the geometry. As you can see, something's wrong. It is wrong because Grasshopper is programmed in a way as when it is operating on two lists, it will match indices for each operation. Meaning, the point with the 0 index will be moved by the vector with the 0 index, 1 with 1, and so on. When it runs out of indices in one but there are still data in the other, the shorter one's last index will get matched with the longer one's remaining entries. Solve this by right-clicking on the motion and turn graph on. What does graph mean? Simple terms, we are transposing the data in the list just like a matrix. Okay. Wherever you graph something in Grasshopper, the program will separate each entry and will move those one level deeper in the data structure. For example, here we have a 0, 0 data structure. A list's data structure or index is shown in the top right corner in curly brackets. At the output, it is 0, 0, 0. That's what I meant by being placed one level deeper. This is the first step, the second, and the third. At this point, the first frame and the rest of the frames are separated. Let's group these with another merge. But by simply merging these together, the difference in the structure that the two lists gives us will result in unnecessary complication in the future, which we do not want. This happens because Grasshopper took the two lists and simply glued them together. The fix is a pretty nifty tool called Path Mapper. Double-clicking on the component, and we type on the left side curly bracket A, curly bracket, on the right the exact same. Return back to the left side, let's write curly bracket A, B, C, curly bracket, turns into curly bracket C plus 1, curly bracket. With this, we are saying that every data block that has an index with a single number can stay that, just like here. Because this is our first frame, it can stay as the first index. For the rest, we are asking Grasshopper to take a look at the last, meaning the deepest part of every single data block. By block I mean these 5 entries, and this 5, and add +1 to the last one. This will be the block's new index. The +1 is required because it starts with a 0 at that level, but 0 is already taken by the first frame and every consecutive frame shall have an index 1 bigger than the previous one. After this, we have multiple options from which we can decide how we want to go on building our structure. First option is to flip the matrix, resulting in points being grouped by their relative position in the frame, meaning instead of being grouped like this, it will be grouped by this. Other than that, we have tree branch and list item. If our goal is to connect multiple points in a repeating fashion, just like in our case, then the easiest and cleanest way, in my opinion, is the flip matrix one. So let's take a flip matrix and connect it. From this, take a line and a shift list. Right click on the wrap menu and set its boolean to false. Take a number 1 and connect it to the shift input. This will tell this component how much it should shift the input list. Connect the flip matrix to the shift list and to the line start point, and then the shift's output to the line's endpoint. It looks good and all, but this is where we get to what I like to call the last line problem. Let's see these lines in a panel. As you can see, there's an invalid line. It is there because with the shift list component, the first point only occurs once, and there is no line going from the last point, hence we don't get an extremely long line connecting the first and the last point. Instead, we get an invalid, which we can easily fix in 3 different ways. Shortest list, clean tree, and colons. Shortest list compares the 2 and trims the longer one. This could be used right before we create the line. Clean tree will simply remove any invalid entry. Here we are going to use the colons because this is the most flexible. Let me show you why. After the flip matrix, take a list length or connect the base number slider into the call frequency and give +1 to it. Flip matrix into a colons list and its output to the start point. With that, the invalid line is gone. Let's imagine a portal frame structure. In a normal case, there should be no lines. At the feet. The removal is easy by taking 3 tree branches with a path 1, 2, and 3. Don't forget to simplify the line's output. With that, only what we need remains. Going from the path mapper, we will need 4 list items to create the columns and the rafters. Actually, we need 5. As for the indices, start from 0 and go all the way to 4 and connect the data into each list. In a panel, we can see that these points are in their own group. Flattening the data will result in these points being in 1 instead. To get the desired geometry, take 4 line components and connect those in the following way. Remember, you can copy with Alt. Connect these one as the start point, with these as the end, this again as the start, and the third one as the end. Be careful here, the next one is tricky. The fourth one will be the start, and the third one will be the end. For the last line, the last list item is the start, and the second to last is the end. On the rafters, usually see the purlins, which we can create in the following way. Thanks to us for the last step, because in that we created the rafters in a way that each and every one's endpoint is the apex, meaning the line's directionality is towards the highest point. This comes in handy in the distribution of the purlins. For that, we have 2 options: divide length or divide curve. Usually distance is what we design around, so let's take 2 divide lengths. It needs a geometry and a number for length. It is another number slider with a name, purlins distance, with a maximum of 5. Connect it to the length and let me show you a trick. Double-clicking on a line creates a relay point with which you can rearrange the wires in your code to make it more visually understandable and more traceable. This has 0 effect on the performance of your code. You can even take a line from that. Take the second and the third line and connect those into the curve. Because this component starts at the start point of a line, meaning here and here, where there is already a line, and we don't want a redundant line, remove those points with call index. Provide the 0 for both, take the points into these components, and we got what we wanted. Then it's flip matrix time, and we do that whole shenanigans once again. Copy this by holding down the Alt key. And got our purlins. This process is the same on the sides. You can do that by taking the 0, 1 and the 3, 4 lines, this, and do that flipping thing again. At this point, we are finished. Yes, you can say that we still need columns which will hold the wall girts and need something to close the two sides. We could do that. Good. One thing that is missing though, which I will show you, is the bracing. Start from the non-flipped output, take 4 tree branches. You can copy with Ctrl+C, Ctrl+V too. For the path, a 0, a 1 up here, and down, let's take the base number value and the value -1. It is subtraction with a 1, and connect that. As for the last, it is the unmodified value itself. If we highlight it, we can see that the last two turns green, meaning it is working fine. And these for the start, just as you would expect. For longer structures, more bracing should be necessary, but applying this logic, you can put additional bracing wherever you want. 2 shift list with 2 lines, wrap to false as usual, branch to the list with a shift amount as 1. Here we are cross-connecting points to get across bracing, meaning the top one's shift as the start and the second one's normal as the end. Then it's second shift with the first one's normal. The method is the exact same on the other end. Pulling out the panel again, you can see that there are 5 lines, but we only needed 4. We solved that with colons and list lengths. Do that for every single one. Ctrl+Shift+V will place the components that are on your clipboard in the middle of the screen, while simple Ctrl+V will place those where they were copied from. Merge these bracings into 2, one on each end. Take a few line components and group it by pressing Ctrl+G. It is a good habit to group the outputs of your script so that you can monitor it if it did do a good job, or so it can easily be connected to other softwares which have a link with Grasshopper, just like Tactile Structures or most of the finite element analysis softwares out there. You can even name it output. With that, we reached the wrapping up point. Let's recap what we have done. Use the basics of Grasshopper to create geometry in 3-dimensional space. Learned how we can operate on lists in a basic way. Flip those to create the skeleton of the structure. Got familiar with the bunch of components of this program, just like the different type of curves and sliders. Last but not least, we learned the basics of engineering a simple portal frame structure. I'm afraid that is all for today. I hope you had fun along the way, or at least learned something new. If you have any question, feel free to leave those down in the comment section or reach out to me directly on any of my socials. Link is down in the description. We will see each other in the next one, but until then, it's a farewell.